Good afternoon and welcome to this video. This is the pre-lab video for experiment called heat of reaction. This is a calorimetry experiment, and the purpose of this video is to kind of go through what that is and get you ready for the pre-lab that is due in advance of that lab coming up. So let's take a look at what it is that we're talking about. What is kind of the fundamental idea behind this lab that we're doing? And so the technique at the heart of the experiment itself here is something called calorimetry. Now, calorimetry is used to do really pretty simple task. We're going to monitor the temperature change that occurs as a chemical reaction takes place. And we can do this, and we do this as a way of trying to measure the enthalpy of the solution and of the chemical reaction as a result. So a couple of things about a calorimeter. A calorimeter can come in a variety of different forms. The one that is most common, the one that we will use, is one that basically looks like a big coffee cup. It's kind of thick-walled styrofoam. But what we do in these reactions is we monitor the temperatures, how they change as we go from beginning of reaction to end of reaction. We monitor the change in temperature, and using an equation that relates the change in temperature to the heat transfer, we're able to calculate the amount of energy that is transferred in the chemical reaction. Now, the way that this works, the way that it utilizes this is through a concept known as heat capacity. Heat capacity, which is given to us by the capital letter C, helps us to measure the energy transfer. Every single material that we have has a known heat capacity. And by definition, the heat capacity is how much energy does it take to raise the temperature of that substance by 1 degree Kelvin. So the upshot of that is we have a very easy transition between energy in joules and temperature change in degrees Celsius or degrees Kelvin. But the problem with heat capacity is that different substance, the same substance can have a different heat capacity based upon its size. And so one way that we standardize heat capacity is through some sort of specialization. We can do what is called a molar heat capacity. This is the capital C with a lowercase or with a subscript m. This is now we're standardizing to a mole. So instead of having a heat capacity that's different for 50 grams and another one for 5 grams and another one for 500 grams, now we can say, okay, if I have a mole of this substance, this is how much energy is going to be transferred for every degree temperature change. Not bad. But we can actually do better. So molar heat capacity has some advantages. It at least gives us something to standardize to. The problem with it is still measuring a mole is not exactly the most easy thing to do. Different substances have different masses associated with them. And again, measuring exactly 1 mole can be kind of problematic. So more often than not, we end up using something called specific heat. Specific heat, that's a C subscript S, is the amount of energy that is required to raise the temperature of 1 gram of substance by 1 degree Celsius or by 1 degree Kelvin. And that works because now we can just measure the mass directly and multiply. So however I multiply the mass times the specific heat, and that'll tell me basically the heat capacity. And if I multiply the heat capacity by the temperature change, that'll tell me how much energy has been transferred. So all the pieces kind of work together here to help us to come to this idea of energy. And so, as I just mentioned, there is a relationship between heat transfer and temperature change using mass and specific heat. And the equation is this: Q, the heat, is equal to M, the mass, times the specific heat of the substance, times the change in temperature. Now, one important thing to note is that if we are at a constant pressure, the value of Q, the heat, is equal to the change in the enthalpy change, the heat of reaction. And so if we are measuring the system and its temperature change, then whatever we get for the value of heat is also the value of delta H. Now, that works really, really well, except for the fact that when we do calorimetry, we're not usually measuring the system. We're measuring the surroundings. The surroundings being the solution that the reaction is taking place in, that's being contained inside of the calorimeter. And so, luckily for us, the relationship between system and surroundings is governed by the first law of thermodynamics. And so we know that all the heat that is absorbed by the system is outputted to the comes from the surroundings and vice versa. So if I know how much heat goes into the surroundings, I know how much heat left the system. It's the same amount, just opposite sides. And so that leaves us with an equation like this. And this is going to be the heart of the reaction of the calculations that you're going to do in the lab. Now we can turn this around. We can find specific heat from quantities of heat being measured just by rearranging this equation. But really at the heart of what we're going to do this particular lab settles around this equation here. And how do we know that we're at constant pressure? Well, because our calorimeter is going to be open to the atmosphere, which means that the pressure is going to be atmospheric pressure, it's going to be held constant. And since we're at constant pressure, the relationship between heat and enthalpy is equivalent. So let's take a look at an example of one of these types of problems. So we're told that the specific heat of octane, C8H18, is 2.22 joules per gram Kelvin. The question is this: how much heat is needed to raise the temperature of 80 grams of octane from 10 degrees to 25 degrees? Well, just if we remember our equation here, this is actually pretty easy. Q, the heat, is equal to M, the mass of the octane, C, the specific heat of the octane, and delta T, the temperature change for the octane. Well, we're told that the mass was 80 grams. We're told that the specific heat is 2.22 joules per gram Kelvin. And the change in temperature, we go from final temperature, 25.0 degrees, to initial temperature, 10.0 degrees. Which if we do the subtraction here, that would mean that we have a value of 15 degrees Celsius for the change in temperature. So Q here would be just the product of those three numbers. So I would take 80 and multiply it by 2.22 and multiply that by 15.0. And I would get, my calculator would spit out 2664 joules to three significant figures. That would round to 2,660 joules. Now note that this is a positive value. This is an endothermic process. And it makes sense because we are raising the temperature. That means that heat is going to have to come into the system to cause the temperature to go up. So we'll skip the second question because it's not as relevant to this particular lab. But that's kind of the calculation that you're going to be doing in this experiment, is these MC delta T kinds of calculations. Now, before we move completely to the experiment itself, let's just talk about the kinds of calorimeters that exist. Now, we've already made mention of what is called a constant pressure calorimeter, also known as a coffee cup calorimeter. This is the kind of calorimeter that we are going to be using in lab. And the reason for it is it's really easy to use, and it's relatively cheap. It's relatively easy to put together. The thing that we have to understand, the thing that we have to know that's really important for us is that when we use coffee cup calorimeters, that means that the reaction itself is being carried out in aqueous solution usually. Aqueous solution is actually part of the surroundings. So the Q values that we calculate for the solution are going to be the opposite of the Q values for the chemical reaction itself. So if the temperature of the solution goes up, that means that for the solution, it was an endothermic process. For the reaction, it's actually an exothermic process, because in order for the solution temperature to go up, that heat had to come from somewhere. That somewhere was the chemical reaction. The chemical reaction generated heat, which was then absorbed by the solution. And since the solution is part of the surroundings, then the relationship here is an opposite relationship. So we've got to be really careful about that kind of calculation. If the temperature of the solution goes up, that means that it's an exothermic process. And if the temperature of the solution goes down, that means it's an endothermic process. So for coffee cup calorimeters, it's kind of different. Now, there is another type of calorimeter here known as constant volume or bomb calorimeter. That's not something that we're going to concern ourselves with here in this class. They are kind of cool, and a lot of really interesting kinds of chemical reactions are done, including those related to like determining nutritional values in food. But that's kind of beyond the scope of our lab. So this is what each one of them looks like. You're going to work with an apparatus very, very similar to this in this lab. Again, this is kind of cool. We use electrical leads to ignite the substance, but everything is kind of self-contained in a bomb calorimeter. All right, let's do one more example, and then we're going to move on to talking more about the specifics of the lab itself. So here we're told that we have a 4.25 gram sample of ammonium nitrate dissolving in 60 grams of water in a coffee cup calorimeter. And the temperature drops from 22 to 16.9 degrees Celsius. Assume that the specific heat of the solution is the same as that of pure water. What we want to know is, what is the heat of reaction for the process of making this solution? So the solution in question here is we've got ammonium nitrate in the solid phase, and we are going to put it into water and turn it into ammonium nitrate in the aqueous phase. So we're going through a phase transition of sorts here. What we want to know is, what is the delta H for this phase transition? Well, since we're doing calorimetry, we can use the MC delta T equation using the values of the solution here to figure out our value of Q. And so Q of solution would be equal to the total mass of the solution. So I got to put both of those together, since when we make the solution, they will both be present. So 64.25 grams of total solution. The specific heat for the solution is 4.184 joules per gram degrees Celsius. And our temperature change, we went from initial temperature is 22, so our final is 16.9. Our initial is 22.0 degrees Celsius. . If I do that subtraction, 16.9 minus 22, I would get a negative 5.1 degrees Celsius. So my Q of solution, 64.25 multiplied by 4.184 multiplied by negative 5.1 would give me a negative to two significant figures, because the temperature change is now only known to two significant figures. This would be negative 1400 joules. Calculator gives me negative 1370.99. But again, I have to round to two significant figures, so that's my second significant figure, the 4. So that gives us a Q of solution. Now remember, the Q of solution in a calorimetry experiment is opposite of the Q of reaction. And the Q of reaction, well, that's the same as the opposite of the heat of reaction as well. So if I've got negative 1400 joules as my heat of solution, that means that my heat of reaction and my enthalpy of reaction would be positive 1400. So there's my delta H for the process, positive 1400. Is the process endothermic or exothermic? Well, because our delta H is positive, that means that heat is coming into the system, which means it's an endothermic process. So I want to talk about one more concept before we get into the experiment itself, and that is Hess's law. Now, Hess's law is kind of something that's running in the background of this experiment. And what I mean by that is, in the end, we're going to try to validate Hess's law, or at least evaluate our data based on Hess's law, because two of the three reactions will add up together to give us the third reaction. And so Hess's law tells us that we can determine the enthalpy for any reaction equation if we have a series of reactions that we can add together. That'll give us the equation that we're interested in. And the best illustration of this actually comes if you look at the discussion here of our experiment here in Lab Archives. Here are the three chemical reactions that you're going to do. You're going to take 10 molar sulfuric acid and react it with 1 molar sodium hydroxide to give us sodium bisulfate in solution. You're also going to take sulfuric acid in the 1 molar concentration and sodium hydroxide in the 1 molar concentration and give us the same product. And we're also going to do a dilution, 10 molar sulfuric acid and 1 molar sulfuric acid. Well, if I look at these three equations side by side by side, what I should be able to recognize is that, well, what do you know? I add these two together, I've got 1 molar sulfuric acid on both sides. They would cancel out. And what's left? 10 molar sulfuric acid, 1 molar sodium hydroxide, and the half molar sodium bisulfate in water solution. So if I know the delta H for reaction number 2, and I know the delta H for reaction number 3, I should be able to add those two together, and the result would give me the enthalpy change for reaction number 1. So that's one of the things that we are testing. We are trying to validate in this experiment, is we're going to use this relationship between reaction 1 and the combination of reactions 2 and 3 to try to determine if our data makes sense. And so that's kind of at the heart of Hess's law. Hess's law says that if I got a bunch of equations that add together, any equation that is generated by the adding together of other equations, the enthalpy for that reaction is going to be the sum of the enthalpies that make up the things that we're adding together. So let's take a look real quick at the Prelab, and we'll kind of wrap this video up. So on the Prelab here, we're talking about, we've got 5 questions. First one was the purpose of the experiment. That you can get right out of the introduction. Kind of infer it based on what it is that we're doing, what we're trying to find. Number 2, why is it important to measure the temperatures of the solutions individually before mixing them together? Well, so one complication of our technique for calorimetry is because the 2 things that we are reacting together are both in solution. And since they're both in solution, we're going to need to calculate their heat changes, their Qs, individually. So I need to know what the change in temperature is for the first solution and what the change in temperature is for the second solution. I'm going to take those 2 solutions, those 2 heat values, and add them together. That's going to give me the total heat of solution for the chemical reaction that took place. So I have to have individual values initially so that I can get those individual heat values. Mentioned this before, number 3. Are we talking about an open, closed, or isolated system? Well, you can make a good argument for open based on the fact that the coffee cups are, largely open. You can make a kind of argument that they're closed if we put some kind of a cover on top of the coffee cup calorimeter to prevent stuff from flying out of there. We can't make an argument for isolated. Remember, isolated systems do not have any energy transfer inside of them, and we are certainly going to experience some heat loss in the use of this calorimeter. That's how they work. I just described what Hess's law is, so you should be able to do that. And then for number 5 is kind of a practice run at the kind of calculation that you're going to have to do. So in this calculation, you are going to have to take your values for solution A and determine the Q for solution A. And you're going to have to take your values for solution B and turn them into a Q for solution B. And so the Q of solution is going to be the sum of QA and QB. And remember, since this is the Q of solution, delta H of the reaction is going to be the opposite of that Q of solution. So hopefully this video helps you at least get started on things. If you do have questions, feel free to stop by my office hours or send me a quick email or text via Remind. I'd be glad to help you kind of get over it and get ready for this lab coming up. But until then, have a great day, and I will see you next time in lab.